You've seen 10,000 dewdrops. You've never actually understood why they're round. Most of us assume a droplet is round because water likes to be round. It feels intuitive. But the real reason involves forces you can't see, and it explains why dew forms the way it does, which is far stranger than you might think. Let's start with the obvious question: where does dew actually come from? Air holds moisture. When temperature drops at night, that moisture can't stay invisible anymore. It has to condense into liquid. But it doesn't condense into a puddle. It condenses into discrete, isolated spheres. Why? The answer begins with surfaces. Water vapor doesn't just condense anywhere. It condenses onto surfaces: grass blades, spider webs, car hoods, window panes. Those surfaces are where the magic starts. But here's the catch. Water doesn't actually want to stick to everything equally. Some surfaces love water, others reject it. Grass loves water. That's why dew clings to grass so readily. But even on a surface that loves water, the droplet doesn't spread out flat. It stays rounded. And that's where surface tension enters the story. Surface tension is the invisible skin that forms on water. It happens because water molecules at the surface pull inward, toward the bulk of the liquid. They're attracted to other water molecules more strongly than they are attracted to air. This creates a kind of elastic membrane. That elastic membrane is crucial. It means the droplet wants to minimize its surface area. And here's a geometric fact. Among all shapes, a sphere has the smallest surface area for any given volume. It's the most efficient shape. Water knows this in a sense. It obeys the laws of physics. So surface tension pulls the droplet inward from all directions equally. The result is a sphere, not because water is trying to be round, but because being round is the path of least resistance. It's the lowest energy state. Physics always takes the easiest route. But here's where it gets more interesting. Not all dewdrops are perfect spheres. Some are slightly flattened. Some cling to the grass at an angle. Why? Because the surface itself matters. The droplet doesn't just sit on top of the grass. It's influenced by the grass's own molecular structure. This is called the contact angle. It's the angle at which the water meets the surface. Some materials create a wide contact angle, water beads up, barely touching. Others create a narrow angle, water spreads out, wetting the surface. Grass falls somewhere in between. So the droplet's shape is a compromise. Surface tension wants a perfect sphere. The surface wants the water to spread. The droplet settles into a shape that balances both forces. It's nearly spherical, close enough for us to call it round. But physics knows the difference. Now, why does dew form in droplets at all, rather than as a uniform film across the grass? That's because uniformity is unstable. If a thin layer of water tried to spread across the entire blade, it would be fighting gravity and surface tension simultaneously. The system would rather collapse into isolated spheres. This is called the Plateau-Rayleigh instability. It's named after two physicists who studied how liquids break apart. Long story short, a thin film of liquid on a surface is thermodynamically unstable. It wants to fragment into droplets. Nature abhors a uniform film. So dew doesn't just condense, it self-organizes. The water vapor condenses onto the grass, surface tension takes hold, and the system naturally fragments into spherical droplets. It's not a design, it's not intentional, it's the inevitable outcome of physics. And here's something that ties it all together. The size of the droplet matters too. Larger droplets are pulled downward by gravity more strongly. That slightly flattens the bottom. Tiny droplets, a fraction of a millimeter, stay nearly perfect spheres. Size and weight change the equation. The smallest dewdrops are nearly invisible to the naked eye. But under a macro lens, they're still there, perfect little spheres. They obey the same laws as the larger droplets you can see. They're just more faithful to the geometry because gravity hasn't had a chance to deform them yet. The same principle applies everywhere water condenses. Fog droplets in the air are spherical. Raindrops start as spheres, though larger ones flatten into hamburger shapes as they fall through air resistance. Even the water inside a cloud is organized into countless tiny spheres. So when you see dew on the grass at dawn, you're not just looking at water, you're looking at physics in action. Every droplet is a small victory of surface tension over chaos. Every sphere is proof that nature follows invisible rules, and those rules are beautiful. You've seen 10,000 dewdrops. Now you know what they are: spheres because surface tension pulls inward, fragments because films are unstable and shaped by the surface beneath them. They're round because being round is the most efficient way to exist. Subscribe to uncover the physics hidden in the everyday. There's a new phenomenon waiting to explain itself every week.